The bacteria in a culture grows by 10% in first 2 hours, decreases by 10% in the next 1 hour, and again increases by 5% in the next 2 hours. If the original count of the bacteria in the sample is 40,000, find the bacteria count at the end of 5 hours. So here at the beginning of the duration, the count of bacteria is given as 40,000. Now this bacteria has been left for 5 hours to be observed. So 1, 2, 3, 4 and 5. Now the bacteria in a culture grows by 10% in the first 2 hours. So basically in the first hour, the bacteria is growing by 10% of 40,000. Now for the second hour also, the bacteria is increasing by 10%. However, this 10% increase is on the count of bacteria which is at the end of first hour. Now we have been given that for the next 1 hour, which is the third hour, the growth decreases by 10%. So this is minus 10%, and this is on the count which is available at the end of the second hour. Now for the next hour, which is the fourth hour, the bacteria increases by 5%. So this is again 5% growth on the count available at the end of third hour and beginning of the fourth hour. And for the fifth hour also, the count is increasing by 5% on the count available at the end of fourth hour. Now we have to find out the count of bacteria at the end of 5 hours. So this count is how much? Now we know that this resembles the scenario of a compound interest, and so we'll use the formula for compound interest and we'll understand how that gets applied to this scenario. So we know for compound interest the count at the end would be denoted as A, and this is equal to P, which is this amount. So let's say this is P, which is the count at the beginning of the culture growth, multiplied by 1 plus R, which is the rate of growth, divided by 100 to the power of n, where n is the number of time periods under consideration. So now A is equal to, so P is 40,000, so 40,000 multiplied by 1 plus, so let's take the first hour. So the first hour the growth is 10%, so rate is 10 divided by 100. So this expresses the growth of bacteria during the first hour. Now the second hour, again the rate of growth is 10%. So that 10% is applicable on the count which is at the end of the first hour. And the count at the end of first hour is this, 40,000 multiplied by 1 plus 10 by 100. So to this I have to multiply 1 plus 10 by 100 because the growth for the second hour is again 10%. So instead what I can do is I can put this as to the power 2. Now let's take the third hour. So in the third hour the growth is minus 10%, and that is on top of the count available at the end of second hour. Now the count available at the end of second hour is this, 40,000 multiplied by 1 plus 10 by 100 square. So this is the count at the end of second hour. Now to this we have to multiply 1 minus 10 by 100 because the growth is negative, so the count is decreasing. Now this represents the count till the end of the third hour. Now for the fourth hour, the count again increases by 5%, and this increases on the count available at the end of the third hour. So on top of this, the growth is 5%, which can be expressed as 1 plus 5 by 100. Now for the fifth hour, the growth is again 5% on top of the count available at the end of 4 hours. So either I can multiply this again by 1 plus 5 by 100, or I can just put a number 2 here, which means 1 plus 5 by 100 square. So this represents the count at the end of fifth hour. So now let's try to solve this. So this is equal to 40,000, 1 plus 0.1 square, and this is 1 minus 0.1 multiplied by 1 plus 0.05 square. So this is equal to 40,000 multiplied by 1.1 square multiplied by 1 minus 0.1 is 0.9 multiplied by 1.05 square. So let me pull my calculator here. So 1.1 square multiplied by 0.9 multiplied by 1.05 square multiplied by 40,000. So this is equal to 48024.9, or we can write as 48025. So this is the count of bacteria at the end of 5 hours.